started doing this a few years ago, and I was just kind of interested in sort of knowing what the sort of earliest application of handwriting recognition that kind of worked a bit was. So any guesses for what kind of year it was from?
1960 something?
That's they started doing something. I found something slightly older, probably not very reliable, but any guesses? What age?
1879.
Not that old. So I found something from 1931, a patent application. But I like it because it kind of shows the importance of machine learning. You've got some training data, which is this wheel of what these examples. You've got some kind of matching algorithm, which is looking at how much light goes through. And you have got a concept of computational complexity. So for each digit you want to recognize, you need to have an extra space in the wheel and one of these things here. So this wouldn't scale up very well if you wanted to do Chinese handwriting recognition, where you've got 4,000 different character classes and substantial variation in writing style. So I'm going to be talking about a certain special type of convolutional network called a spatially sparse convolutional network. This is a basic convolutional network that you all know of. And what we're talking about is basically mathematically equivalent, but it allows you to design the network slightly differently in practice, which means you can approach problems a bit differently. So here you just have sort of two layers of pooling, and this is kind of what people use for a long time. So in 2004, Jan Kuhn wanted to do object recognition at a scale of 96 by 96, and he did that with just two layers of pooling, and it worked, but it wasn't deep yet. One of the first kind of deep networks that people used was in Schmidt-Charles, et al. So they used 4 layers of pooling, and the kind of interesting thing is they use very small filters, so like C3, C2, 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 and that worked well for things like MNIST, Chinese handwriting recognition, a scale of 40 by 40, a bit of padding, and also for say CFAR10. So there are lots of different kind of pieces of software for running convolutional networks. So it's CUDA-ConvNet, Caffe, Torch, Dieleman, which has various front ends, TensorFlow, which also has a front end in Gruss, MacConvNet, CUDNN. In fact, there's a lot of overlap because a lot of those packages actually use the CUDNN kernel. So, mathematically they're doing exactly the same thing. So there's just lots of people interested in it. So people have built lots of different sort of software packages. And my one's kind of slightly different. So there's kind of the entire world of people doing ConvNet, and then there's me, basically. But it can apply to a range of problems. There are about 10 posters on the wall, and I reckon about maybe 4 of them could use sparse ConvNets. So 60% of you can ignore this talk, and the other 40%, it's like that might be applicable. So when I say sparse, it's not sparse in feature space, it's spatially sparse. So it's if you have some kind of problem where some of the pixels are not interesting for some reason, like it's blank paper or something like that, then this technique can, it's the same as running a normal convolutional network, but you can maybe scale the data up a bit bigger and so maybe get better accuracy. So why spatially sparse convolutional networks? Partly it's just getting the word sparse, putting it in front of ConvNets and seeing if that's a research topic. Also, if you kind of think about something like online handwriting, so when it comes to handwriting recognition, there's 2 types, there's online and offline. Offline is where you just get the picture, and you have to treat it like a picture. Online is where you actually are using something like an iPad, so you get the trace of the person's finger or the pen on the digitizer, so you actually get a one-dimensional manifold embedded in 2-dimensional space. And if you think about it, if you want to increase the resolution in which you're processing that, if you double the resolution, is that going to be linear or quadratic in the computational time? If you're using a normal convolutional network, then if you double the linear scale, you get 4 times the area, and so it takes 4 times as long to run. Whereas if you do something that respects the sparsity of the space, then it will just double the complexity. So it's much easier to increase the accuracy by increasing the scale. And that's particularly important for, say, Chinese and Japanese kind of scripts. Another advantage is you can very easily do data augmentation, because the processing time only really depends on the thing you're pushing into the network, so you can put lots of padding in, and that can improve accuracy. whereas with the normal convolutional network, if you added padding, that would massively increase the runtime. You can deal with inputs that are different sizes, so if you want to say crop a picture and look at just a piece of it, you could do that efficiently. In machine learning, there's something called the curse of dimensionality, which is normally interpreted as being a bad thing. Basically, if you want to do kind of nearest neighbor matching in high dimensional spaces, it doesn't work because however many data points you have, they're going to be far apart. But that kind of actually works the opposite way when it comes to sparsity for convolutional networks. If you have something which is, say, 2D, like a character, it might be a bit sparse, but it won't be terribly sparse because there's just not much space in 2 dimensions for the ink to spread out on the page. Whereas if you have something like maybe a model in 3D, there's much more space, much more potential for the input to be sparse because there's just more space. Similarly, if you went to say 4D or 5D even, that would give you an even stronger effect. And it's worth bearing in mind that 3D space includes 2-dimensional space with space-time, so you have 1 and 2 space dimensions, 1 time dimension, or 4D space includes 3-dimensional space with space-time, so if you wanted to have, say, maybe an aeroplane circling around an airport waiting to land, that would be like a 4D path. Well, it's in 4-dimensional space, but it's a 1D manifold, so you should be able to process it efficiently using some technique which could be fast complex. So for online handwriting recognition, you've got a path which is a bunch of X and Y coordinates, and you want to recognize what it is. So each character is made up of strokes, and each stroke is a list of X, Y coordinates. And it can be hard if there's a small number of training samples per class, or if there are lots of classes, or if there's lots of variation between writers. And ideally, you want to make this as efficient as possible so it can run on a slightly low-powered device like a phone or an iPad. So the simple strategy is just to trace the characters, and then you get a picture which you can put into a convolutional network. You can also try adding value-added information to the thing if you're doing that. So you could have like some sense of what direction the pen was moving in, and add that to the representation. And what I wanted to do was sort of combine both to efficiently recognize handwriting. So these are some samples from the Assamese alphabet. It's publicly available. So 183 different characters. It's an Indian language, and there are only, I had to split them later up. So I used 36 examples for training and 9 examples per class for testing. These are some training characters. So there are about 4,000 different classes and about 240 for training for each class. And then you can see there's quite a lot of variation between writers. So one sort of thing that isn't really discussed very much, but I think is interesting, is how does the choice of the networks kind of change what kind of thing you'll recognise? So this is kind of a made-up language where you've got 3 different things. So how many different characters do you think I have?
4.
Well, there's no blank characters. Okay, so it could be 1, it could be 2, it could be 3, depending on whether or not it's significant that there's a small space here and a big space here, or whether it's significant that the lines above or below. So depending on how you do the pooling, that might just fundamentally affect what the network can recognise. So it's important to kind of think about what kind of prior information you're building into your classifier by choosing the structure the way you do. And with handwriting recognition, you kind of want it to be very elastic, because elastic deformations of a character will probably be the same character for any reasonable alphabet, and small rotations will not affect the meaning, large rotations will. So I took the network of tree hugger and just added a few more layers of max pooling, or an extra layer of max pooling to make it 96 by 96, and I wanted to compare it to the Lynette 7 network that Jan Pan was using for object recognition. So what I wanted to do was just count the number of different ways of going through the network, just to kind of get a sense for how information is flowing up. So this is with 2 layers of max pooling, quite large. This is with 5 layers of max pooling, and you can see because of the pooling, the way the pooling is being done, there are lots more ways of navigating, of information to navigate through the network with more layers of pooling. aspect, but you can see that the more layers of pooling, perhaps the more elastic kind of invariance would be built into the network. So looking at the Indian characters, the SMEs, I just wanted to see what the effect would be of increasing the scale. So just putting the characters in and doing low data augmentation, you can see the benefit of increasing the scale. So it goes from about 50% error down to about 14% error. And adding translations is very useful. So it's surprising that adding translations is helpful because if you think about it, when you take a character and you translate the input, you're producing something that can't possibly be in the testing data because you're always going to center the testing data. But even just moving the input character around into a completely unrealistic part of the input field dramatically reduces the error rate, and if you add fine transformations, slanting and skewing, then you reduce it even more. So basically, you can go from what looks like a very hard problem to a very easy problem just by making a really large input field and using lots of data augmentation. Okay, so for Chinese handwriting, the kind of state-of-the-art before people started using Comprehensible was, for this particular data set, was about 8% error. Winiger used characters that sort of scale 40 by 40, and I got an error rate of 5.61 with data augmentation and everything else. Adding a few layers of max pooling and using sparsity gets the error rate down to 3.82, and using a particular type of max pooling that works well with sparse convolutional networks, you can get the error rate down even a bit more. And sparse convolutional networks are currently being used in, there's like a Android and iOS app which uses sparsity to do character recognition for Chinese. So CFAR 10, it's a data set of small pictures, there are 10 classes. So it looks like a dense data set because it's just regular images, but using sparsity to make it cheap to do lots of data augmentation, I managed to reduce the error rate from 11.21, which is what Winiger got, down to 3.47. And for reference, humans are about 6% error rate, so convolutional networks are doing substantially better than humans on this data set, like quite a few. And this competition was mentioned before, so I came third, so worse than other people, but I did some work after the competition to kind of improve the solution, and I'm now working with the oceanographers at the National Observatory Oceanography, to put this into the ecotaxa web application for biologists. And the advantage is you've got lots of pictures of varying sizes, and most of the pictures are quite small, so it's much more efficient if you just process the small ones, the small scale and the big ones at a big scale, and that's also can help with the accuracy. And you can get quite good results with just one network. So it's easy to use in practice. I also tried using it for medical imaging. So this is a different type of competition. So these are pictures of people's eyes levels, the retina, and it's trying to look for signs of bleeding that are indicative that they might lose their sight soon. I just removed the mean from each picture to produce something which is sparse, so grey is the background colour, and then I had to process the stuff in the middle. And there was a particular metric for the competition called Cohen's kappa. I came in first place with a score of 0.85. Interestingly, if you took the top two solutions, you get a kappa score of 0.92, which suggests that the computers are doing better than the people, and actually there's kind of like a average label you can detect, which is better than what the people are doing. Because if you test the same person on the same image 2 days apart, they're not very reliable. And if you look at two people working in the same lab sitting at neighbouring desks, they're also not very reliable. So computers can kind of average out the training labels to produce a more consistent classification. It can also potentially be used for, say, 3D data. So this is from an MRI scan, which is in regions sparse. Other possible applications include things like you've got chemistry. So you might have an atom, which is you have different types of molecule, which has different types of atoms in. So you can encode them using one-point encoding, and then try and predict chemical properties like with relation to it, NMR experiments. Or you can look at a protein and try and predict the function. And there, being sparse is an advantage because you don't have to process all the empty space. So sparsity for convolutional networks is a bit like sparsity for matrix multiplication in that you're doing the same mathematical operation, but it's just you carry it out slightly differently by keeping track of where the information belongs, and instead of having a completely regular operation, so matrix multiplication is totally regular if you do it in the dense setting, but if you do it in the sparse setting, you need to kind of keep track of extra information for where the data lives. So with matrix multiplication, it's no good having 50% sparsity. That wouldn't be very efficient because you'd still need to keep track of every piece of information and where it is. So you'd actually be doing, if you tried to use sparse matrix multiplication with 50% sparsity, that would be no good. But with convolutional networks, it's actually much better because you have, for each location, you have a large feature vector. You only need to store once where that feature vector belongs to. So even if you only have a bit of sparsity, it still, can be an advantage computationally. So you might want to design the network to take into account how sparsity kind of changes as you go through a network. So small filters tend to work well, or you can slightly change the rules for how information calculates through the network. So this is just like a very simple Python class for doing a fully connected network, just kind of for reference. So when you're doing forward propagation, you've got forward step, which is a matrix multiplication, and you've got backward step where you calculate the derivative of the cost function with respect to the weight parameter, and then you send backwards the you apply the chain rule to work out the send back an error signal. So in order to implement this sparse way, we need to have just basically a method with forward and backward paths. So this is how convolutional networks are implemented in the dense setting. So you have some input data, which is something like this. And one way of doing it is by lowering, which means you take the input image, and for every output site, you gather together all the information that can affect the output there, and then it basically reduces the problem into a matrix multiplication. So if you're doing maybe a 3x3 filter, and you have maybe 16 input features, then you take a 3x3x16 box that will affect the output. You gather all those features together, 3x3x16, you do a matrix multiplication, and that produces one output point, so one output vector. So this is how you work in the dense case. So basically you do a bit of shuffling about, and then you get a matrix multiplication operation. And the good thing about GPUs is they're very efficient at doing matrix multiplication. And so basically if we can reduce sparse convolutional networks to a matrix multiplication, then it will run efficiently. Okay, so how does sparsity work in a convolutional network? So you can't quite see the background very clearly, but these are kind of these represent different layers of the network. So on the left you have maybe the input image, which might be a circle. And then, first of all, imagine you had a completely blank input to a convolutional network. As you went up through the network, because the input's translation invariant, the higher layers would also be translation invariant. So if you had a completely blank input to a convolutional network, you could work out what the output would be with just, working out one pixel for each of the hidden layers. So if you disturb that by having a few active pixels, then you only need to calculate you only need to change certain, you only need to calculate the values at certain points higher up. So as we go along, this is like a convolution operation, and that slightly thickens the number of sites you need to calculate, because you've got like the box shifting over the thin line, and then you do make a pooling operation, which then greatly reduces the number of active sites, and so sparsity is slightly disappearing as you go through the network, but at the lower levels, which are probably the most computation intensive, you get a big saving if you have sparsity. And you can do the same thing in, say, 3D. So if you've got a 3D convolutional network, this is a representation of a knot. This kind of corresponds to doing a convolution. This corresponds to doing a pooling operation. And you can see that sparsity is preserved in the early layers of the network. So if you have sparse 3D data, that will stay sparse as you go up there. If, however, you used a very big filter, then this would get much thicker, so you want to avoid doing that. So we say that a site is active if it can somehow see something in the input, so if the value is different to the ground state you would get if you had a completely blank input. And obviously the cost of calculating this is going to depend on the number of active sites per image. So to implement this, you just gather up all the information in the same way you would do in the dense case, but instead of having every site in the output being active, you only have some sites being active, so you only calculate a fraction of the output sites, and that basically saves you amount of time proportional to the percentage of active sites. And calculating which sites are active you can do offline, away from the GPU, so that's basically free. Another interesting thing, maybe, is that convolutional networks are generally done in a kind of on a square grid and in 3 dimensions on a cubic grid, but there's no fundamental reason why you have to. And if you want to go to higher dimensions, then it might make sense to change the lattice you're working on. So in 2 dimensions, the smallest useful filter you can have is 2 by 2, so that's 4 sites per filter. Whereas if you go to 3 dimensions, then you need to double the number of filters to 8, and if you went to 4 dimensions, you'd have to double again to 16. So the number of sites per filter would be 2 to the d, which is growing very quickly. Whereas if you go to maybe a triangular or tetrahedral or hypertetrahedral lattice, then you can have just d plus 1 site per filter, so you can go to higher dimensions without having to deal with absolutely massive small filters. Perhaps quite surprisingly, changing from a square grid to a triangular grid really doesn't affect the performance of CNNs in any meaningful way. They just kind of, they produce very similar performance. So these are kind of networks that are chosen to be quite similar. The triangular ones obviously have 3/4 as many parameters because there's less work to do. The amount of work is kind of a bit unpredictable because of the way changing the lattice kind of changes how many active sites you might have. So this is for CFAR 10. But generally speaking, you save time and you have pretty much the same accuracy. So, for example, you can use sparse convolutional networks for 3D object recognition. So these are from the Shrek 2015 dataset, which is from the competition. The competition is meant for doing unsupervised learning, but I just used it in a supervised way for simplicity. So these are 4 examples of snake class, and these are different categories: ant, elephant, robot, and tortoise. To make sure I was recognizing things in a totally 3D way, I just took each model and randomly rotated it each time, so I couldn't rely on the orientation, just the 3D structure. And by choosing an appropriate input scale and some type of pooling, I could get pretty much perfect accuracy, so at 99% very easily. So these are a few different types of pooling. This is on a tetrahedral lattice, this is on a cubic lattice, this is using fractional max pooling. So there's a trade-off between the accuracy and the computational cost, but you can get quite good accuracy relatively cheaply. So roughly speaking, one image net application would be kind of here, so it's not massive computational cost. apply it to maybe other things like object recognition. So if you have a video, then you can just look at which pixels are changing over time, so from one slide to another, and that produces a sparse 2 plus 1 dimensional data set. You have 2 spatial dimensions, 1 time dimension, and you can do object recognition on that. And yeah. Here's another data set, so it's the color, the input color, so it's a bit less sparse, but it's still quite sparse if you focus on threshold, and you can still recognize reasonably well what's going on. With video recognition, you can just use a 2D slice and work, look at that. But the best method is to use a combination of different techniques, and this is just using one method, and it's reasonably accurate. Okay. So thank you for listening, and I'll stop there. Any questions?
Do you get any advantage from the fact that the rectified linear units make half your samples sparse?
So it's not sparsity in the feature space, it's sparsity in spatial sense. So if you think about so when you have a convolutional network, if it's a two-dimensional spatial, if it's a two-dimensional convolutional network, then each hidden layer and input layer is a three-dimensional array. So you've got the 2 spatial dimensions and you've got the feature dimension as well. And I'm only interested in the sparsity in the feature in the spatial sense. So with respect to the 2 spatial dimensions, not the feature dimension. So what sigmoid function you use isn't going to have any impact on the speed. Just the percentage of
Surely it makes each layer more sparse.
That's but it's
Spatially.
Well, no, because as long as some of the sites are, so you might say 32 features and if 16 are on, 16 are off, then you're basically doing them vectored by matrix multiplication, and so you have to do the whole thing. So it doesn't really save you anything there. But it's the spatial sparsity that saves you time. And if you have a time dimension, then you also save with regards to sparsity there.
Are there any sort of architectures of this mapped onto like FPGA?
Well, it's basically, computation is just a matrix. You